This talk is a kind of survey of ideas, so we'll see how it goes. I wanted to begin by making some remarks about Kelvin and the vortex atoms, as you know. You know the story, but this YouTube video is worth seeing if you haven't seen it before, and it lasts about a minute, and it's self-explanatory. It's self-explanatory, except I would like to know how the dolphins are actually doing that. They seem to turn their head in a certain way, and the little vortex ring appears, and then they play with it, as you see. So that's the first research question in this talk, is what are those dolphins doing? See, they can get some dynamics before the things blow up on them. Okay, and then of course there were Kelvin's. Here's a little tidbit that you might not have encountered. You all know about Kelvin's vortex theory, but then some people who were theosophists got interested in that theory, and they made up their own pictures of what the vortex atom ought to look like, the one that would be significant for them. And this picture came down through time from Leadbetter and Besant, who were theosophists. And I thought it was an intriguing picture, and I'm not sure even if it's knotted. You'd have to look very carefully. But I noticed that in my computer doodlings, there were some things that looked similar to their vortex atom, like this, for example. This is a Fourier knot given in terms of sines and cosines, and it looks somewhat similar. It's interesting. Of course, they had the idea of knots as being abstract forms that could be instantiated physically, but their notion of the abstract was perhaps a little different from ours. And then another curious bit of the history of this is that Leadbetter and Besant promoted that atom that I showed you before as what they had seen clairvoyantly, but in fact a man named Babbitt had earlier written a book with a much more complex knot, which he undoubtedly was associating with Kelvin, but he was also a theosophist or some person of that sort. And if you look at his picture, you see that he has various electrical sort of designations on this knot and so on. I wouldn't know what to make of it otherwise, but it is electrical. As you see, globally, it has a negative and a positive end and so on. And then getting back to circularity, which is prior to knotting, of course. Knots are embeddings of circles in three-dimensional space. There is the mythology of that, such as the Ouroboros, the world snake, the universe that is eating its own tail. Or even in these modern days of multiple universes, there is in the mythology mutuality in the form of multiple Ouroboros. And then there are very general ideas about knots, and I'm going to talk about some general ideas in a moment, very general, but this is perhaps the most general concrete idea about a knot, that it's information that's independent of the substrate that carries it. And that makes it interesting for thinking analogically about lots of things, that the knot itself doesn't depend on what it's made out of. And yet, of course, if you want to think about it physically, it does depend on what it's made out of, and the thickness of that, and the properties of that. But as a topological or abstract pattern, it doesn't depend. And then getting back to circularity in the Ouroboros, I always like to think about this symbol of John Wheeler's, which represents the universe observing the Big Bang over there on the right, and U is the universe, which came slowly into being able to observe itself. But it's a quantum paradox because, particularly according to Wheeler, a phenomenon is not an actual phenomenon until it is an observed phenomenon. And until it is actual, it is in the potential. So the universe, what was the state of the universe before the universe was able to observe itself, is Wheeler's paradox. And I like to cartoon this by making a knotted Wheeler universe, which adds an extra question, which is, in what the question actually is, although symbolized by the knot, the question is, in what context was the previous question being asked about the universe? And a knot is always a phenomenon that occurs in a context. In the abstract, there's no knot. It only happens because of the embedding in three-dimensional space. Now I'm going to become abstract, and I want to talk about the interface between topology and logic, or the interface between topology and set theory, because a lot of topological things that we use are actually geometric or topological instantiations of some kind of a connection that is really a logical connection. You might think on that. You know lots of examples. For example, graph theory, as originated by Euler, was the idea of having points, and those points are either connected to one another or they're not. Quite abstract. And if you look at Euler's original paper, although it was derived from a picture of bridges, the notion of the graph was the modern notion, abstract notion of points and relations. Then we always think of a graph in terms of its topological realization, in terms of edges, but the edges being topological spaces and actually usually real line intervals are much, much more complicated than the graph itself. So there are always these logical interrelationships, and this one is perhaps a little bit unusual, but it's interesting to follow it for thinking about the structure of knot diagrams. So, is that the wrong button there? Yeah. So I'm going to represent membership by one line crossing over another line. Both lines are labeled entirely A or B. And that line A, although it has a break in it, is thought to be connected and running underneath B, of course. That's the interpretation of a crossing. And the line A or the line B might go anywhere else that it liked. Or it might have ends, or it might not have ends in these diagrams. So it's just an asymmetrical relationship. A is under B and will be said to be a member of B. What could you do with that? Well, you could make some renegade sets like this one. Here's omega, and omega is a member of omega, as you see, and it's the only member of omega. And so this is a set that's a member of itself. So the sets that we might depict with these diagrams are not Venn diagrams and can violate some of the usual tenets of set theory. Of course, it's okay to have sets that are members of themselves. They're called non-well-founded to put a little suspicion around them, but they're all right. You just have to handle them in the right way. This is one way to think about them. And then if you did do that and cross it with topology, you would get a curious situation, because you would have a depiction where A belongs to A, if and only if, by topological move, A does not belong to A. So that's no longer troublesome in the representation. I'm not sure if Russell was happy with that or not in the pictures above. So here are some knot sets. Again, the self-membering one, but mutuality. A is a member of B and B is a member of A. You can have that. You can also write down standard sets. I guess I didn't make a slide of one of those. And then you can ask how it interacts with the topology. And in this case, you see that you have to change your notion of sets a little bit in order for them to act well with the topology. You see, because B here, up in the top of the slide, consists of two copies of A. It has membership of A twice. A is twice a member of B. But if you were allowing topological move, then B could slide right out and leave A empty and B empty, and so that ought to be an equivalence, which means that multiple appearances of A and B can be canceled in pairs. So in a certain sense, knot sets are fermionic. Identical elements will cancel. But there's no problem with invariance under the third Reidemeister move, so this is a topological theory of non-standard sets. Or rather, we could extrapolate it into one. So that's one way of thinking about. Was there a question?
Yeah, question. So again, I realize you're being somewhat poetic, but should I think of that canceling as adjacent things? Is it an ordering?
You're asking me whether maybe I could make something out of the fermionic at that point. I have not made any physics out of that particular remark about fermionics. So at the moment, it's a poetic. Remark.
Whether these are unordered or ordered, or is ordering important in the adjacent?
Well, yeah. Now, I didn't want to go on putting more structure on knots, but I do like to think that this is the most elementary topological invariant situation that I can look at with regard to knot diagrams. But because of the double cancellations, it's only working mod 2, and it will see some linking numbers. It will see some concatenated linking numbers, but it won't see the Borromean rings. It won't see the knotting of the trefoil knot. And so if you wanted to start here and imagine putting more structure in to get more invariance, then you would want to start ordering things, okay? And at that point, you could imagine reinventing some of the known knot invariants, like the fundamental group or the quandle. But I didn't want to go there. I just wanted to illustrate this. Okay. And then there are when you look at other topological questions, like the linkedness of the Borromean rings, we can prove that they're linked by doing some things along the lines that I just mentioned, fundamental group, quandle, other forms of coloring, using ordering, or not polynomials. But if you were to just be naive and look at the Borromean rings, the thing that strikes you at first is that red surrounds blue, blue surrounds green, or yellow, depending on how you look at that. I guess it's green to me. And green surrounds red. So it's a scissors, paper, stone pattern. And surely that's fundamental in why they're linked. But when you start proving it, you kind of lose the sense of that in most of the proofs. I wouldn't say you lose it in all of them, because by the time you start thinking about things like higher order linking numbers, which will occur here, and Massey products and things like that, then the fact that they're in that geometric relationship to one another is in fact important. So it's interesting to look at knot theory with a very elementary eye. That's the main point here, and with a diagrammatic eye. Now I want to shift to quantum things and to a question that I like, and that is, should there be a relationship between quantum entanglement and topological entanglement? We had back here a good example of topological entanglement. And there are simpler ones as well, but this is the one I have in mind. The Borromean rings are certainly entangled. You can't pull them apart. They also have the property that if you remove any one of the rings, of course, they go apart. Quantum entanglement is another matter, so it seems. This is an example of an entangled state, 0 and 1 being basis elements for a vector space. And the Dirac bracket there means 0 tensor 1, and the other one means 1 tensor 0. And this is a state living in a tensor product of a qubit space with itself, a qubit space having basis 0 and 1, the smallest kind of quantum information space. So this state is entangled in the sense that it cannot be written as the tensor product of two qubits. And also in the sense that being what it is, if you were to observe it, you could observe it perhaps for what is happening in the first tensor factor, but if you did that, you would land on either 0, 1 or 1, 0. You can't help it. So that the other tensor factor is forced into becoming whatever it becomes when you observe the first tensor factor. Observing the first tensor factor could happen far away from observing the second tensor factor if the state were distributed, and this is an example of quantum entanglement, where observing over here on the left will create a state which has changed to a particular predictable thing on the right, far away, as though an influence was carried from one part to the other. It's partly because of the abstraction of this, but it is a puzzle, what's going on with that. The abstraction is that no space was being written about when you talked about the quantum state. Well, Aravind made an interesting suggestion that suggests relating topology and entanglement. His suggestion was that the GHZ state, the state here, 000 minus 111, that one, by the way, just look at it for a moment. You observe it and it goes into 0, 0 or 1, 1, depending on what happens. And that doesn't matter whether you observed in the first, second, or third tensor factors. So it becomes unentangled whenever you observe it, but in and of itself, it's entangled. A nice example. And Aravind suggested that it was rather like the Borromean rings, which, when you cut any one of the rings away, would become unentangled. So you could start making catalogs of links that are analogous to quantum states, but what that would actually mean in terms of the foundations of quantum theory is a good question. So that's a nice question. I like the question. There are some difficulties with the question as you start to look at it. One of them would be a state like this. This state, I mean the second line in my slide, this state is entangled. It's not a tensor product. On the other hand, if you were to notice what happens if you observe in the first tensor factor. There are two possibilities. Either you get 0, 0 and a 1. 1 is what you observed, and the remaining state is in 0, 0. Or what is that thing? Or you got 1, 0 plus 0, 1, because that's what remains when you knock out the 0. You can see why he's thinking knock it out, because that's how you observe. You see, you just knock out the 0 in that tensor factor and take what remains, which is 1, 0 and 0, 1. But that guy is entangled. So depending on how you observe, depending on what happens when you observe it, you either get entangled or not entangled. You don't get a specific thing. Whereas if you started with a link, which is a classical entity, and you remove a component, the remaining link is either entangled or it's not entangled. It isn't with some probability one way and some probability another way. So that makes a difficulty in comparing the way quantum states behave and the way knots and links behave. In this way, we can make a case for having knots which have some quantum properties. So you could or else adding more mechanism to Aravind. I'm not sure which would be better, but I suspect that making the knots have quantum properties would be better. Now here's our Borromean rings, and I put an arrow from blue over to the other remaining two components and an arrow from each of them. And then that arrow, in the way we described it, is a kind of probabilistic arrow. With 50-50 probability, that arrow is going to switch the crossing when you eliminate blue. And then that funny knot with probabilistic arrows, that would behave the way the quantum state behaved. So you could do that. You could add some extra mechanism. Or you could imagine knots that are superpositions of different kinds of topology, which is another idea. So that would be a quantum knot. A quantum knot, that blob up there, is not knotted or unknotted. It's not known until you observe it. And then when you observe it, it becomes a particular topology, like the one on the bottom of the slide. So then a quantum knot would be a superposition of some knots, and those knots would be classical types. Or they would be classical representatives for knot types. Because when you're doing topology, you immediately run into that. You run into when I talk about a knot, am I talking about the specific representative of the knot, like a particular rope in a particular form, or am I talking about its topologist knot type, which is anybody that could be deformed into the one you're looking at? So you could do it either way, and Sam Lamonaco and I have been thinking about this, and we agree that we want to be able to do it both ways. But I haven't indicated which way it would be here. But here's an example of a superposition, and when you observe it, maybe it gives you K, or maybe it gives you K prime. It'll only, if it's a quantum situation of a classical sort, it'll only give you one or the other. It won't give you both. It's like Schrodinger's cat. It's either alive or it's dead. It's either the trefoil or it's the figure 8, a more innocuous version of Schrodinger's cat. And then you can do things with this. For example, you could make a universal quantum knot. You could take the superposition of representatives of all possible knot types. It's countable. And take a superposition of all of them with some phases and have a strange quantum knot state like that. And then you could imagine getting information about that by observing it in one way or another. You think that's about as crazy an idea as you've heard so far today, but there's a paper called On Quantum Money by Peter Shor and Edward Farhi, in which they use exactly that idea to try to instantiate a very secure piece of quantum information. And the way they do it is they take a superposition of all knot types that have a given Alexander polynomial. You, the owner of the money, know the Alexander polynomial, but what you don't know is the state. And then there are ways to test whether the state is valid or not, but it would be very hard to produce the state. So hard that I'm a little skeptical that they could produce, that the Mint could make the state that Shor and Farhi like. But this idea of creating things which contain a lot of very hard to understand information is maybe useful. Here's a quick take on how we're thinking about quantum knots when we want to represent them as specific diagrams or specific three-dimensional configurations. We make them out of mosaics like this, so that the tiny ingredients of the brew are these little squares, of which there are only a few. And that's the base space. The base space is a Hilbert space whose basis is these types. And then when you look at one of these, this is actually the tensor product of these tiles in the order left to right and going lexicographically, and living in a larger space. And then the picture becomes a certain vector in a Hilbert space. And another picture is another vector, and you can form superpositions of things or observables and do all the usual standard quantum mechanics with this, and think about knot information. So that's a possibility. Now I'm changing topics, but I used the idea of a knot drawn on a mosaic to shift this pictorially. Here's a knot. It's actually a trefoil knot, and it's been woven on the surface of a rhombic triacontahedron. And it's part of the geometry that Bob Gray and Lynn Claire Dennis are studying for their own reasons. And then having brought in polyhedra, I go to another scientific question. And this one is perhaps well known to you. Is the geometric universe a Poincare dodecahedral space? Or in other words, is that by the geometric universe, I mean you have a single time snapshot of the whole universe. And if you want a definition of that, you will have to think about it carefully, because there is no single time for the whole universe. But you imagine that you have the universe at one time, one geometric piece that describes the whole universe. And then it might be a compact three-manifold, and it might be our favorite compact three-manifold, the dodecahedral space, which has been speculated on by Luminet and Jeff Weeks and other people. This is a beautiful three-manifold, which is obtained by taking opposite faces of a dodecahedron and identifying them. Maybe the universe is actually the dodecahedral space. And that would look like this, you see. If you wanted to see exactly what it was, that's exactly what it is. This tells you how to identify the opposite faces. What does this have to do with knot theory? Well, the dodecahedral space has axes of symmetry, a five-fold that I've illustrated, three-fold and two-fold axes of symmetry. And if you were to take the five-fold axis of symmetry as a point to talk about, and mod out by the cyclic action of the group of order 5, you would get an orbit space. That orbit space is the three-sphere, and the axis, which is a circle, goes down to a trefoil knot. So in other words, the dodecahedral space is the five-fold cyclic branch covering of the three-sphere branched along the trefoil knot. Another way of seeing it more symmetrically is to understand it as a certain algebraic variety, but I won't go into it. The point is that if the universe were a dodecahedral space, then the universe would be directly related to the trefoil knot. So that is why I would like the universe to be the dodecahedral space. But now let's go on to another topic. As you see, this is topical about knots in relation to physics, and gets to particles after a little while. We're finally getting to particles with this rather remarkable paper by Herbert Yela, which happened a long time ago, and is related to a lot of the themes that are in this conference. He wrote a paper about which he called Flux Quantization and Particle Physics, and he suggested that quantized electromagnetic flux could model elementary particles. And in his theory, the trefoil knot represented a neutrino, and a mirror image of the trefoil knot represented an antineutrino. And he thought about quarks and other things in terms of his flux loops, and it was quite interesting. I met him back in the middle 1970s at a topology conference. He was probably in his 70s at that time. And he carried a clutch of catheter tubes on his belt with which he could make knots that modeled all these ideas. Not so much came from those papers of his at that time, but maybe more will come now. Then in more modern times, and now I'm mentioning some things that are going to be gone into in much more detail here. I just thought it would be fun to mention them. It's been suggested and is being investigated by people who are here, like Tom Keppert and Roman Buini, that flux tubes related to quarks, gluon flux tubes, might become knotted, and that the least length of the knot that is obtained by such a method, that is, you can try to tie a knot in a rope and get the least length you can, but those least lengths are related to the energy levels. So this is an interesting website. You might take note of that. It has illustrations of how gluon fields work. Just to give you an example, if it works, yeah, like that. And there are other people who are also working on this. Here's one of the older papers of Tom and Roman. And knot theorists who are interested in rope length have gotten into this line of research and are working with them. And I'm going to just give you a quick illustration of this problem of rope length using a film of Jason Cantarella's. Here's the knot 942, as it's depicted by a program that draws some knots by Rob Sherine. But this is not the least length representation of the 942. In order to do that, you would have to pull it up tight. And Jason's program does a nice job of that. And his website has lots and lots of illustrations of this process. So you can give a knot to this program and let it work on it, and it will pull it up, and it won't. And it will also handle, tubes around the knot. So you end up in the end with a knot with a certain tube diameter and a certain length. And then you can read it from the program what the tube diameter and the length is and take the ratio of the length to the tube diameter, and that's a scale-free number, which may or may not, from the experimental data of the program, be the rope length. But it would be an approximation to the rope length. That is the minimal one that you could possibly get for that knot. And this has something to do with energy levels in this physical possibility. So that's that one. Here's another one of a flakier nature, a paper I found by someone who suggests that an electron might be a photon with a toroidal topology, and he has illustrations like this. Twisting band for the electromagnetic field. Here's another one which I think is very interesting. This was published in the Knot Theory Journal by Mr. Avrin here. And his model is very simple. He has his Mobius bands with 3 half twists, and then there are a number of different possibilities for the way you can place the twists. And these particles, made of Mobius bands, interact by fusing, like I've illustrated here on the right-hand side. And he matches these with fermions. So the interactions are like this, fusions of this sort. And you can get particle interactions like this. Here's a neutron Mobius, which topologically deforms and then unfuses into 3, and it corresponds in this patterning to a neutron going to a proton, an electron, and an electron neutrino. That's his system. And he manages pretty well with this system without a lot of other mathematics. Just curious. So there's Escher's Mobius band, which is perhaps the best image of this particular notion. We're going to have to maybe skip something. But here's another paper that I found interesting. This one by Batty-Pratt and Racy was written a long time ago, as you see. And they decided that they wanted to take seriously the Dirac string trick. Now, for them, taking seriously the Dirac string trick means that they would like to think that an electron actually is, in some way, through the space, connected to its surround. And then, just as in the belt trick, and maybe I'll skip forward so you know what I'm talking about if you don't have the terminology of the belt trick. In the belt trick, you have a belt attached between an inner sphere and an outer concentric sphere. And it is twisted by 720 degrees, and we are going to allow it to deform, but it is anchored to the inner sphere and it is anchored to the outer sphere. You can easily demonstrate this with a belt, but we'll leave it up on the slide. You push it around the sphere, comes back, and the twist is gone. Okay? That's the belt trick. It corresponds to saying that if you were to turn by 720 degrees, something changes. If you were to turn by 360 degrees, something changes. But if you were to turn by 720 degrees, you're back where you started. And if you are observing a fermion and you walk around a fermion and come back, then the quantum wave function for the fermion changes sign by 1 phase shift, minus. If you go around twice, you're back to where you started. That's the belt trick. And it is indeed related to this geometry. But it's usually understood to be related to this geometry by the way I just described it. In order to do a quantum process, you need to move a vector in S by an action of SU2. Well, where's SU2? Well, SU2 is covering twice the rotations of three-dimensional space. So if you were to rotate in three-dimensional space, that will get covered if it's a quantum process by an element in SU2, but it could end up on the other sheet, and that's where the minus sign comes from. The homotopy you see here has to do with the topology of SO3. So all of this gets explained in the usual way by having ordinary space with its rotation symmetries and SO3 or SU2 in relation to them, but outside of space and part of the apparatus of the physics. But these people are arguing that physics is one thing and the relationship with the space ought to be somehow intrinsic to the physics, and they analyze the Dirac equation and show how to match it up with quaternion operators that are related to the twisting of the electrons' strands that go to the walls. They would like it to be real. Nobody knows how to make it real. Nobody knows how to change the definition of three space so all this would work. But the mechanism can be made to happen by having the rotations happen in just the right way, so that as the ball, the electron ball, keeps rotating around, every 720 degrees it comes back to where it started. So that's an interesting speculation about the nature of space itself. Here I've illustrated, but I'll skip it, the way you can see how quaternion operators correspond to rotations around different directions, which gives you part of the story of the relationship with SU2. We're verging on the end, but I have a couple more things to say, so I will do it by skipping a bit. There is knot theory with its Reidemeister moves. With those moves of Reidemeister, you have a complete theory of knots and links in principle. Two knots and links are equivalent if you can get from one, or links are equivalent if you can get from one to the other by a sequence of these diagrammatic moves. A lot of invariants are based on the properties of those moves. On the physics side, there was Penrose's theory of spin networks, which is related to the SU2 that I just mentioned. And that theory of spin networks was originally in place because one was looking for a new way to think about space-time. Not exactly like Batty-Pratt, but a new way to think about space-time that would incorporate the SU2 into the space-time. One can deform those networks so that they're more topological. This slide is too complicated, but I'm going to say something about a couple of features of it. In deforming the networks, you put the Jones polynomial down in the bottom of the network to keep track of what the topology is doing. And you have particles which are interacting, and the particles are various amounts of spin. They interact, an A and a B, to produce another particle, C. And they can braid now. You can have a braiding between the particles. You can have a twist around like that, and that will be represented in the system because of the deformation of the networks. So you can have braided networks. You can have particles that are changing when you move them around one another by some phase other than plus or minus 1. And this can be understood in terms of the topology of knot invariance, among other things. And people have tried to use this for the sake of producing quantum systems that could be controlled. One of the systems that is very interesting is the quantum Hall effect, where you have the possibility of vortices in the plane of electrons, and those quasi-particles, the vortices, can braid one another and acquire phase. I see that I'm out of time, so that's one theme, and I would have talked about it for a while, and we're going to just sort of go quickly to the end. So you see how this theme would have looked. Or maybe I will stop here. I think I will stop here with the following remark that's interesting. There's more. One of the simplest kinds of particle interactions for thinking about quantum Hall effect and the braiding that happens is to use a very, very simple particle, a kind of abstract Majorana fermion, which interacts with itself either to produce itself or to produce nothing. That one is sufficient at the particle level to have some braiding and do the kind of job that one is interested in. If you wanted to get a picture of what such a thing would look like, this is a nice picture. Two circles interacting, if they are outside one another and they bump into one another, they could merge and produce one. If one of them was concentrically inside the other and expanded, it could just make it disappear like that. So that's one way of thinking about it. That way of thinking about it turns out to be, if you made a little formal system out of those circles, turns out to be a form of elementary logic. It's like truth tables. A circle around a circle turns it into nothing, and that's like negation. And a circle next to a circle producing a circle is like A or A is equal to A. And so this formal system can be used for logic. And so logic and particles come together, but these particles can be braided and produce a very beautiful model that is enough to do quantum computing. And I'm just going to go to there and stop. In this model, using that elementary particle, there is basic braiding that can be used to produce enough unitary transformations to, in principle, do quantum mechanics or quantum computing. And so there's a very elementary particle which presumably actually exists as a kind of a vortex in quantum Hall systems. And we'll stop there because I should have stopped 3 minutes ago.
Comments?
Yes.
Does this view, do you think, provide any insight into any of the foundational issues?
Speak up, please.
Does this particular approach provide any new insight into the foundational issues in quantum mechanics, or is it just sort of a transformation of variables?
Are you asking whether this provides new insight?
Taking a topological sort of not approach.
I'm taking your question, and I may not have heard the whole question, but I'm taking your question to be, does this provide new insight into quantum mechanics? And it could be, that question could be landing on various parts of the talk, so let's have it land on this part of the talk.
Sure.
So what happens here is that you show that certain braid group representations are sufficient to produce unitary transformations in general, using enough linear algebra to make them up. I think that ought to be an insight into physics, but I'm not sure I understand what it's telling me, right? It is telling me that if I wish to make a finite dimensional quantum process, I can, in principle, draw braid and make it represent that process up to any degree of approximation. It tells me that I can build a topological computer that's universal. But what does that say about the nature of quantum mechanics itself, that the unitary groups can be densely represented by the braid groups? I don't know. I would like to think that it says more than just the fact that it's possible that we might make a quantum computer by using something as delicate as the quantum Hall effect. I would like it to say something fundamental about quantum physics itself. So I have the same question you do. I've amplified your question. I haven't answered it.
Any other questions? Well, if not, let's thank Will again.